Welcome back to The Explainer. I gotta tell you, I am absolutely buzzing about today's topic because we're not just looking at the cosmos today, we're talking about unlocking a completely new sense to experience it. For all of human history, we've been stuck just looking up at the stars. But today, we're diving into how humanity literally learned to listen. Okay, so just sit with this question for a second. What if we could actually hear the universe? For thousands of years, our grasp of the cosmos depended entirely on our eyes, on light. From the earliest stargazers all the way to the James Webb Space Telescope, we've basically been watching a beautifully shot but totally silent film. But here's the mind-bending part. The universe is not silent. Not at all. We just didn't have the ears to listen to it yet. If you think about traditional electromagnetic astronomy, it's pretty much like sight. It's obviously incredible, but light has flaws. It gets blocked, scattered, or absorbed by all that cosmic dust and gas out there. There are huge, dense pockets of the universe we just can't see. But gravitational wave astronomy, that's way more like sound. These waves just cruise straight through everything. They travel from the absolute darkest, dustiest corners of the universe completely unimpeded, bringing us this pristine, raw data that light just can't touch. So let's talk about what these ripples in space-time actually are and how Albert Einstein basically called this over a century ago. Way back in 1916, Einstein predicted gravitational waves as part of his general theory of relativity. He figured out that gravity isn't just some invisible magnetic-like pull, it's the literal curvature of space-time itself. Imagine the universe is a super calm pond. If you chuck a massive boulder in there, it creates ripples that carry energy outward, right? Gravitational waves are those ripples, just minute distortions in the actual geometry of space and time, blasting outward at the speed of light. But, we aren't talking about throwing rocks in a pond here. To generate these waves, you need the most unimaginably violent, chaotic events possible. We're talking massive black holes locked in a death spiral, ultra-dense neutron stars smashing into each other, dying stars going supernova, and maybe even the chaotic residual echoes of the Big Bang itself. Which obviously brings up a huge question. If these cosmic smash-ups are so insanely violent, why did it take a whole century after Einstein to actually catch one? Well, measuring the unimaginably small is no easy feat. To actually catch these waves, we had to build absolute engineering marvels, places like LIGO in the US, Virgo in Italy, and Kagra in Japan. These interferometers work by taking a single laser beam and splitting it down two 2.5-mile-long vacuum tubes set up in an L shape. The light bounces off these perfectly positioned mirrors at the far ends and comes back to recombine. Now, normally, the light waves cancel each other out perfectly in what's called destructive interference. But when a gravitational wave rolls through Earth, it literally stretches space in one direction and squishes it in the other. That tiny, tiny shift changes the distance the laser travels, messes with the interference pattern, and boom, creates a flash of light we can measure. Now, by the time these ripples cross millions of light years to reach us, they are insanely weak. To even spot them, these observatories have to measure a physical change in those 2.5-mile arms that is smaller than the width of a single proton. Seriously, less than a proton. We are detecting the most brutal collisions in the universe by measuring the smallest physical changes conceivable here on Earth. It is hands down one of the greatest scientific flexes of the 21st century, all kicking off with that first direct detection back in 2015. And that crazy sensitivity, it's catapulted us into a whole new era of ringing black holes. With the latest GWTC-5 catalog data dropping, precision gravitational astronomy is officially here. Just get a load of this number. 390. That's how many confirmed gravitational wave events humanity has banked since that very first one. Because we keep upgrading the detectors, we aren't just sitting around crossing our fingers for a signal anymore. This global network is snatching up 3 or 4 new cosmic collisions every single week. But out of that massive haul of data, there is one event, GW250114, that just completely broke the mold. It hit a signal-to-noise ratio of 76.9, meaning it absolutely sliced through all the background static. It's the absolute loudest, clearest gravitational wave signal we have ever recorded, and it came from 2 black holes smashing together over 1 billion light-years away. So why do we care if the signal is loud? Well, Cornell physicist Keith Mittman has this brilliant analogy. He explains that when 2 black holes merge, the collision rings like a bell, emitting specific tones. In physics jargon, these are called quasi-normal modes. Because this particular signal was just so pristine, scientists could actually isolate these multiple tones ringing out from the newly formed black hole. That let them do something called black hole spectroscopy, And the payoff was massive. They proved this final black hole behaves exactly, and I mean exactly, the way Einstein's relativity said it would. Plus, they used these tones to verify Stephen Hawking's black hole area theorem, proving with crazy precision that the total surface area of a black hole's event horizon really does go up after a merger. We're not just taking Einstein or Hawking's word for it anymore, we are literally stress testing the fundamental laws of physics in the most extreme environments imaginable.
Oh, and the same catalog uncovered something else totally wild: second-generation black holes. By looking at how insanely fast these things were spinning, researchers figured out they aren't just collapsed stars. They're the leftover remnants of previous black hole collisions. It shows that in really crowded cosmic neighborhoods, like dense stellar clusters, these monsters are just continually finding each other and merging all over again.
All of this feeds right into a massive paradigm shift. Welcome to the multi-messenger era, where we're finally combining cosmic sight and cosmic sound. If you trace the timeline, it is wild how fast this field is moving. From Einstein just doing the math in 1916 to that historic first detection in 2015, but the real game changer hit in 2017. An event named GW 170817 fundamentally changed astronomy forever. Here's why that event was such a huge deal. It wasn't black holes colliding. It was two ultra-dense neutron stars. And because they're actually made of matter, their collision didn't just send out gravitational waves we could feel. It blasted out an insane amount of light, a kilonova, that telescopes all over the world could actually see. By feeling the ripples and seeing the light at the exact same time, astronomers finally proved that these violent neutron star smash-ups are the cosmic forges creating the universe's heavy elements. Seriously, if you've got a gold ring on right now, that material was almost certainly forged in a collision exactly like this one.
And this tag-team multi-messenger approach is stepping up to solve one of the biggest headaches in cosmology right now: the Hubble tension. We all know the universe is expanding, right? But our traditional ways of measuring how fast it's expanding keep giving us conflicting answers. Now, gravitational waves are acting as this totally independent referee. Thanks to incredible sky localizations, like a recent event that pinpointed a collision to a tiny little 6-square-degree patch of the sky, we are dialing in the expansion rate. The latest data just bumped our precision up by 25%, getting us that much closer to finally solving this massive puzzle.
So, where exactly do we go from here? Unlocking the ultimate mysteries of the universe requires looking at the future of our cosmic hearing. And I promise you, what's on the horizon is going to absolutely blow your mind. We are right on the edge of rolling out third-generation detectors. Imagine ditching our current setups for massive subterranean observatories, like the upcoming Einstein telescope. Or, even crazier, getting off Earth altogether. The LISA mission is going to be a space-based interferometer with arms that are literally millions of miles long. It sounds absurd, I know, but that immense scale is exactly what we need to pick up the deep, low-frequency rumbles of supermassive black holes colliding literally anywhere in the universe. With those next-gen ears, we're moving way beyond just hunting for black holes. We'll be using gravitational waves as the ultimate skeleton key. We're talking about hunting down the true nature of dark matter, figuring out what dark energy even is, and testing physics way beyond the standard model. See, because gravitational waves pass through absolutely everything without getting messed up, they are the only messenger that can reach us all the way from the dawn of time. Which leaves us with this final, genuinely breathtaking question. As our cosmic hearing gets sharper and sharper, we might actually detect primordial waves one day, that background hum generated in the very first trillionth of a second of the universe's existence. What hidden messages are just waiting for us in the echoes of the Big Bang itself? When we can actually sit back and listen to the very birth of the universe, there is no telling what kind of secrets we're going to uncover. Thank you so much for hanging out with me on this explainer. Keep your ears to the cosmos, and I'll catch you next time.